Hello everyone! Today Raquel and I are going to be talking to you about X-ray production. Throughout our career, we hope to assist patients with the knowledge we will acquire in the field by assisting the medical team in taking precise medical images, also known as X-rays, in order to obtain a more reliable understanding of the patient's condition. As a radiographer, our responsibility will be to appropriately communicate with patients about their X-ray procedures. So in order to take good X-rays, we must learn and understand the concept well of what an X-ray is and how X-rays are produced. Let's start off with how X-rays were discovered. X-rays were actually discovered by Wilhelm Röntgen in November 8, 1895, while using cathode rays that led him to unknown form of X-ray radiation. While using the cathode rays to picture his wife's hands, Wilhelm saw an image appear showing his wife's bones of her hand. This was the very first human being image to be created. So he had called these images X-rays. X because in mathematics it is commonly used to indicate an unknown quantity. Although known as Röntgen rays, he preferred the term X-rays. X-rays today are commonly known as medical images taken to diagnose any type of abnormality within a patient. An X-ray is actually an excellent tool for the determination of a wide variety of issues and, as a matter of fact, are produced in a standard way. With this being said, today there are two types of interactions that are known for X-ray production. And they are a characteristic interaction and a Bremsstrahlung interaction. I am going to briefly discuss how Bremsstrahlung works. Bremsstrahlung, in simple terms, means deceleration radiation of a charged particle. When producing X-ray photons, Bremsstrahlung is the most likely to be in effect because it can happen at less than 70 kbp, and I will explain to you why this is. During this interaction, the positive attraction of the nucleus causes deceleration of the incoming fast electrons while passing the atomic nucleus. The slowing down of these incoming electrons represents a reduction of kinetic energy, which is energy in motion at full speed, and that energy lost is released as an X-ray photon. The closer a fast electron approaches to the nucleus with full energy, the greater will be the deceleration of the electron. When an incoming electron coming in at full speed comes to a complete stop at the nuclear force field, 100% of that energy lost from the electron produces an X-ray photon. More kinetic energy is produced when the slowing down of the incident electron coming in at full speed is higher. Moreover, when the electron passes closer to the nucleus, the energy of the X-ray produced will be higher. So the stronger an electron is while approaching the nucleus, the closer the attraction is of producing an X-ray. I hope all of you have understood how Bremsstrahlung works, and now it is time to introduce the characteristic interaction.
Characteristic interaction is the direct opposite of Bremsstrahlung. Unlike Bremsstrahlung, characteristic means to accelerate radiation. In the generation of these X-rays, appropriately accelerated electrons or protons striking at a target can eject the orbital electrons of the atoms. Characteristic X-rays depend on the difference in energy levels between the orbital shells of the atom. The differences between binding energy of each shell determines the discrete energy of the X-rays produced. Binding energy is defined as the quantity of energy which its electrons are held in position by the attraction of the nucleus. Characteristic radiation only composes a small portion of the X-ray beam, despite the significance in high energies of penetration. The negative charge of a projectile electron ejects an orbital electron out of the orbit. This leaves an empty space in the electron shell of the atom. The atom which is left with a positive charge will eventually pull in another electron to return to its natural state. Until then, the empty space created in that specific shell will be filled by any electron available from higher orbits. As the atom tries to return to its ground state, which is the state with the least energy, electrons from the outer orbits will fall down into the vacancies that are closer to the nucleus. There's a reduction of the energy when an outer orbit pulls toward an inner orbit. According to the laws of conservation of energy, the potential energy is required to convert to another form of energy but cannot disappear. And that is how characteristic X rays are produced. In 1913, the X-ray tube was introduced to the world by Dr. William Coolidge. The discovery of the X-ray by Röntgen influenced him to start experimenting on his own. In the X-ray tube, the evacuated discharge tube is the surrounding glass. The tungsten filament is fused to the tube as shown. The filament is covered with barium oxide, which makes it easier for tungsten to emit electrons. The filament becomes heated with the aid of a DC circuit. The DC circuit is consisted of a battery, an ammeter, and a rheostat. The hollow part that surrounds the filament, which is a cylindrical shield, maintains a negative potential that focuses the electrons that is emitted by the filament into the anode. The tungsten block is used as the anode and it is held in an angle of 45 degrees. The anode is emitted in the copper log and is connected to a copper rod. There is an arrangement to cool the copper rod. The anode and the cathode are connected with the positive and negative terminals of a high tension supply. The production of X-rays begin with the tungsten filament being heated by an electrical current. The filaments then emit electrons. The cylindrical shield helps focus the electrons emitted from the filament onto the point of the anode. The negative charge of the cylindrical shield forces the electrons to come merge onto the point of the anode. The electrons strike the anode with a large amount of kinetic energy. The major part of the energy of the incident electrons convert into heat and the remaining parts appear in the form of X-rays. This is how a circuit is usually set up, the cathode side being negative and the anode side being positive. A heated cathode produces electrons. The electrons are then accelerated by high voltage towards a middle target. Upon collision, electrons are decelerated, then emit an electromagnetic radiation in the form of X-rays. X-rays are mainly used in the field of medicine to diagnose and to treat any abnormality or disease. X-rays have many uses outside of a hospital or medical facility as well. They can also detect flaws or cracks in certain finished goods, such as airplanes or cars. They can also differentiate between real and fake diamonds. X-rays are used to study the structure of crystals as well. Lastly, X-rays can be used as metal detectors. Throughout the years in medicine, there have been significant changes pertaining to technology. In X-ray technology, however, there were some minor changes. In 1895, one experimental accident created one of the biggest milestones in medical history with the invention of X-rays. X-rays are electromagnetic waves with much higher energies than light and most other forms of electromagnetic radiation. As mentioned before, to generate these magnetic waves, electrons emitted from the X-ray tube filament must acquire extreme amounts of kinetic energy by the time they strike the anode disk. The two common interactions are known as Bremsstrahlung and characteristic. Although they are inversely proportional to each other, they are both very essential to the X-ray production. This is why these two interactions are critical in radiology and have a major contribution to X-ray production.